So let's look at Chapter 8, Section 8.2, Angular Velocity and Angular Acceleration. So average angular velocity is angular displacement over time, which is theta over t, and it's commonly seen as radians per second squared. Instantaneous angular velocity is just angular velocity at any given instant. It could be positive or negative, and it's called the instantaneous angular velocity, or speed. So if a rotating object has a constant angular velocity, then the instantaneous and the average velocity are going to be the same. So then we're going to look at angular acceleration, which is basically just the changing angular velocity. So just how it is in linear, how it's a changing linear velocity, it's the same concept. So if there's a changing angular velocity, it means that there has to be an angular acceleration. That means it's not constant or zero. So average angular acceleration is change of angular velocity over time, which is alpha equals w over t, and it's commonly seen as radians per second squared. So common examples you will get when it's asking for angular acceleration would be a compact disc rotating continuously decreases, or an electric blender changes speed from low to high. So if there's any changing in velocity, if it's going higher, if it's going faster and slower, then there has to be an angular acceleration. If the acceleration is constant or zero, you can still use kinematic equations or the big five. So in your formula sheet, you'll see that it's just the same thing for the big five. It's just changing in letters or variables. So it's called the big rotational five. So alpha will be seen as a, w will be seen as v, time will still be time, and theta will equal x. Let's check our understanding. If a pair of scissors is being used to cut a piece of paper in half, does each blade of the scissors have the same angular velocity, both magnitude and direction, at a given instant? And the answer would be no. Why? If they're giving me the same angular velocity, you would think so, but no. Just because the instantaneous w, or velocity, of each is the same, it doesn't mean that they're going to be going in the same direction, because as you know in angular displacement, that they're going to be rotating in opposite directions. Now let's look at this problem. If the Earth is spinning on its axis once a day and orbits the Sun once a year, 365 1/4 days, determine the average angular velocity in radians per second of the Earth as it is when it spins on its axis and when it orbits the Sun. In each case, take the positive direction for the angular displacement to be the direction of the Earth's motion. So they're already telling you that positive direction of the angular displacement, and they're giving us both the initial angle theta and the final angle theta for the chart. So if w equals theta over time, and we're just going to look at the speed of it, we already know because 1 revolution is 2 pi radian, and they're asking for its spin on this axis, which means that it's going through a full rotation, and you just have to keep in mind the time. So for this, if we just spin on its axis, it takes 1 day, so we have to convert that into seconds. So 1 day equals 24 hours, and 1 hour equals 360 seconds. So you're just dividing 2 pi by that, and it will give you 7.3 times 10 to the negative fifth radians per second. And it's very similar for b as well, but we're just going to have to look at a bigger time. So if w equals theta over time, but it's for the orbit, 2 pi is still, you could still use 2 pi because obviously it's still one rotation, but it's just for the orbiting. But time will be different because now you have to keep in mind that it's 365 1/4 days, not 1 day. So you just have to change the times, and you would multiply still by 24 and 360 seconds, and you would get 2.0 times 10 to the negative 7th radians per second. And the final one, if a Ferris wheel rotates on an angular velocity of 0.24 radians per second, and it's starting from rest, so it's giving us already our initial velocity of 0, it reaches its operating speed with an average angular acceleration of 0.030 radians per second squared. So you already know the acceleration is not constant, that it's changing from slower to faster. So we already know our final velocity because of 0.24 radians per second, and we already know our initial by 0, we already know our acceleration, and we just have to find time. So one of the formulas we can use, and it's seen in your linear kinematics as velocity final equals velocity initial plus acceleration times t, but this time it would just be w final equals w initial plus alpha t. So you just plug in those numbers, which would give you 0.24 equals 0 plus 0.030 time, and you just divide 0.24 divided by 0.030, and if you put that in your calculator, it's going to give you time is 8 seconds. So throughout this whole time, when we were learning velocity and acceleration, we just have to keep in mind that it's the same concept as linear. You're just going to be using W for velocity and alpha for A, and the same thing that whether or not alpha is constant or zero, or if it's changing because of the changing velocity, that it's still the same thing, you're just changing your variables. And that's 8.2.